Hello, boys and girls. Welcome back to another edition of Crush Lusher Television. All right, so here is part 2 of continuity. So we did it before when we had the graphs like this. What part were continuous, what parts were not, and all the different ways that a graph can not be continuous. But what happens if the octopus steals the graph? Uh-oh. No graph stealing. I'm watching you, octopus. Oh my God. Okay. So we have this right here. What do we need to do? Well, we need to do a few things. And it all comes with a proof. Because see this where it says justify your answer? You have to be able to explain and prove. You can't just say yes or no. Okay, so I'm going to show you how to do it step by step. Make sure you take all good notes. Here you go. So, here's a piecewise function. And here's your title. Pause the video if you need to write it down. Okay, so is this graph continuous at x equals 3? So you see that there's some sort of break there. So if I was to draw a little sketchy sketch at 3, anything less than 3, you have this upside down parabola. Anything greater than 3, you have this line, like that. So how do you know that you can draw a straight line from the upside down parabola to the line? How do you know that they're connected in some way? Well, in order to do that, we need to prove some stuff. The first thing you need to do is we get to prove the limit as x approaches 3 from the left of f of x equals the limit as x approaches 3 from the right of f of x. Why do we have to prove the limit? So that we don't get a jump. Because when you have a jump discontinuity, sort of like this, so it's at x equals 4, the limit from the left does not equal the limit from the right. So if the limit from the left and limit from the right do not equal each other, they have a different y value, then I know immediately that it's not continuous, that I have to pick up my pencil. I have a jump. Okay, so let's see that first. So the limit as x approaches 3 from the left. So this is the left. So that's going to be the limit. And all these notes, I want you to take them exactly like I do. Yeah, I'm writing stuff down multiple times. But yeah, this is what you have to do. You've got to be very precise. Limit as x approaches 3 from the... This is a question mark, by the way. Is this... I don't know. Is this equal? Limit as x approaches 3 from the left of f of x. So that's going to be negative 1 times 3 squared plus 6. So that's 9. Negative 9 plus 6, which is negative 3. Okay. So as we're approaching the graph on the parabola, the y value is going to be negative 3. So how about from the right? So the limit as x approaches 3 from the right of f of x. So that's going to be from the right. I'm approaching 3 from the right. So I'm going to go on here. So that's 2 times 3 minus 8. So that's going to be 2 times 3, which is 6, minus 8, which is negative 2. Uh-oh. What have we just discovered? What type of discontinuity is this? Yeah, it's a jump discontinuity. Why? Because when you have this parabola, when you get to x equals 3, something like this, when you get to x equals 3, you're approaching negative 3, but the line starts at negative 2. So there's a jump right here. So this is going to start at, the parabola goes to negative 3, and the line starts at negative 2. So there's a jump discontinuity here. Cool. All right, don't work. That's all right. So we got a concluding statement. No, and always write the concluding statement. F of x is not continuous at x equals 3 because the limit as x approaches 3 from the left of f of x does not equal the limit as x approaches 3 from the right of f of x. Boom. There's my justification, and here's all my work. There's my proof I got. Cool. Let's try another one. Let's try another one. Here you go. Let's get my paper down. Here you go. Okay, so we do the second one. Here it is. It looks like this on the paper. Here it is. So we have f of x, and we have x plus 1, and we have x squared plus 1. So we have it breaking at 1 is a continuous at 1, justify your answer. So write that down. Cool, cool, cool. All right. So So at 1, it breaks. So I have this line here when x is less than 1 or equal to 1. And then when x is greater than 1, we have the parabola. Okay. So first step, I'm going to put Roman number 1. Is there a jump in the graph or not? Let's see. The limit as x approaches 1 from the left of f of x. Does that equal the limit as x approaches 1 from the right of f of x? Okay, let's try it. So the limit as x approaches 1 from the left of f of x. 1 from the left will be on this side because x is less than 1. So that's going to be 1 plus 1, which is 2. Easy. All right. The limit as x approaches 1 from the right of f of x. From the right, you are approaching, getting really, really close to 1. You're still on this parabola. So that's going to be 1 squared plus 1, which is also 2. Cool. Ding, 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 ding. What does that mean? Well, the limit as x approaches 1 from both directions of f of x equals 2. Cool. So now we have a legitimate limit right here. So, does that mean it's continuous? Then we can write it without picking up our pencil? Not necessarily yet. Why not? Well, let's go back to our picture. So, in this case, we have, this is a jump. So we know that there's not a jump because we're approaching the same y value from the left and the right. But, look at this at x equals 2. You have the same limit here, right? So the limit as x approaches from the left and the right as x equals 2 equals -1. But is it continuous? No, because there's a hole right there. So how do we make sure that there's not a hole in the graph right here? Well, we got to find that the value itself at x equals 2 does in fact equal the same thing as the limit. And it doesn't equal something different like it does up here, like x equals 3. So we got to make sure that the value, let's go back to this actually. So now part 2 of my proof, does the limit as x approaches 1 from both directions, does that equal the actual point? So because the limit has to equal the point so that I can just draw it straight up like this. So if the limit approaches 1 from both directions, I need to make sure the point is there too. And there's not just a point somewhere up the hill, up over here or over here, that doesn't matter. So I'm going to make sure that the point is the same as the limit from the left and the right, so I can just draw it nicely without picking up my pencil. Okay, so we know that this is 2. We got that from the last part, f of 1. So I go back to my original problem. Where is it equal on the domain? That's right here, so I do this. Yeah, it's redundant, but I'm going to do it anyway. F of 1 equals this part here, so it's 1 plus 1. Is 2. Bam. So no, got it. So this in fact is continuous. Here's your concluding statement. Memorize this, copy it down, don't get fancy, just write down what I write down, alright? Yes, f of x is continuous at x equals 1 because, I'm just going to write this last part here, this should be a question mark, sorry, the limit as x approaches 1 from both directions of f of x equals the point at f of 1. So that's the full definition. So there you go. So here's my proof, here's my justification, and here's my concluding statement. Got it. Make your paper look like mine. One more. Here you go. All right, f of x equals, so we have 3 when x equals 2, and 2x minus 3 if x does not equal 2. Is it continuous at x equals 2? Justify your answer. There should be exclamation point. There you go. So justification, part 1. You know what I'm doing. There's no surprises. Here's the third time. So the limit as x approaches 2 from the left of f of x, does that equal the limit as x approaches 2 from the right of f of x? Well, if I draw my little chart here, so 2, something's going on. When x equals 2, graph is 3. When x does not equal 2, which means every other thing, like -1, 0, infinity, whatever, so it means over here and here, that's when x does not equal 2. We have this line. Okay? So the limit as x approaches 2 from the left of f of x, that's going to be on this side right here. So it's going to be 2 times 2 minus 3. 4 minus 3, which is 1. Got it. And then the limit as x approaches 2 from the right of f of x is going to be, same thing. 2 times 2 minus 3. 4 minus 3 is 1. Ding, 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 ding. So we've proven that the limit as x approaches 2 from both directions of f of x equals 1. So we've proven that we're going from the left and the right. Bam, bam. We have the same limit, but do we have a hole? Do we have removal discontinuity or not? We got to make sure that the point is the same thing. So part 2 of my proof. Does the limit as x approaches 2 of f of x equal the point at 2? Well, we have the limit as x approaches 2 of f of x equals 1. We just did that. F of 2 equals, 3. No. So this looks like we just had a removable discontinuity. So the point is not where the limit is. That's what we just proved. So this has a little bit of a hole right there. So it looks something like this. So, no concluding statement. F of x is not continuous at x equals 2 because, please spell out because, it's really easy to do. The limit as x approaches 2 of f of x does not equal f of 2. The limit does not equal the point, so therefore we have a removable discontinuity. Done. Okay. Nice job. Nice job. Okay, so now what we got to do? We got to, scrolling. You have to do these 2 problems right here. So, pause the video, knock these out. Are they continuous? And this is going to be at x equals 0 and x equals 1. It doesn't say, but yeah, that's where it should be. When the graph breaks, that's where you're deciding. So see if you can do 13 and 14 right now. Pause the video. Great job. Good work, everybody.